Objective 3.1, Nth roots and rational exponents. In Chapter 3, we will be looking at another type of function that involves roots and rational exponents or fractional exponents. And so our first lesson here today is taking a look at what those things are and a little bit about how they work. So our objective today is to be able to evaluate the nth root of real numbers using both radical notation and rational exponent notation. So a little bit of vocabulary to start. It says for an integer n greater than 1, if b to the n power equals a, then we would say b is the nth root of a. So when we ask ourselves what kind of root we want and what the answer is going to be, we kind of need to think about what would the number be that if I took it to that nth power, I would get the a that's inside of my radical sign. And it goes on to say that an nth root of a is written using the radical sign. And you'll notice that in the little dip there, where we don't normally have anything written when we're talking about square roots. Well, if it's something other than a square root, then we need a number there to indicate what kind of root we're taking. And that number is called the index of the radical. Okay, so if we see a number there, we know we're dealing with some other kind of root besides just a square root. So here's how radical notation and exponential notation are related to each other. If using the radical, we see that we have the nth root, then in exponential form, that is the same as saying we're taking a and raising it to the 1 over n power. Okay, these two notations are equivalent. It's just a matter of form, whether we're writing it in radical form or whether we're writing it in exponential form. So a couple of examples would be if I was taking the cube root of 8, that would be the same as 8 to the 1/3 power. Or if I was taking the fourth root of x, I could rewrite that as x to the 1/4 power. So it's the denominator of the fraction that matches with the index of the radical. A few rules that we need to follow when we're working with these. The first rule is that if n is odd, so the root that we're taking is odd, then we can expect there to only be one real nth root. So if I'm taking the cubed root or the fifth root of something, there should only be one real root for the answer. If n is even, however, then we have some different possibilities. So if n is even and my a is positive, then I would have two real nth roots. Notice that plus or minus out in front. That should look familiar from the square rooting that we've been working with. So that indicates that we have two real nth roots. If n is even and a ends up being equal to 0, then the a has only one real nth root, and it's going to be 0. If n is even and a is less than 0, then a has no real nth roots. We would have complex nth roots, but we're not going to have any real nth roots. Now, what we have to keep in mind is that even though a may have two roots, we don't always use both of them. So for example, if n is even, square root, fourth root, sixth root, and a is greater than 0, something positive, then we just got done saying that a would have two real nth roots. But there's two different situations where this could come up, and that's going to dictate just how many of those roots we're really interested in. One situation is if we are trying to just evaluate or simplify the expression. And the other situation is if we're actually taking a square root or a fourth root or some even root as a step in solving an equation. So when we just want to evaluate or simplify, we're really only interested in the positive, or what's called the principal square root. But when we're taking the root on both sides as part of solving an equation, then we want to know both the positive and the negative roots because both are possible solutions. So that's the difference between when we just use one root and when we use both. So here's our first example in actually being able to evaluate nth roots. And notice we are being asked to evaluate. So even if we're talking about an even root, we're only looking for one answer. Okay, so in the first example, we're looking at the cubed root of 64. So again, based on our definition at the beginning, what we want to be thinking about is what is the number that if I cube it, I would get the 64. And that number is going to be a 4, because 4 to the third power gives you the 64 that's inside the radical sign. Now in the next example, we have 25 to the 1/2 power. If it helps, we can think of that as the square root of 25 using the equivalent form. And then it becomes fairly obvious that that's going to be an answer of 5. In the third example, we have a negative fifth root of 32. So again, think about what number, if I take it to the fifth power, would give me the 32 that's inside of the radical. But then the negative on the outside of the radical means that I take that answer, which was 2, and I make it negative. Okay? Now, that was just looking at having some kind of number in the denominator and taking a particular root. But we can also have exponents where the fraction has a number in the numerator other than 1, as well as a number in the denominator. And when that happens, this is telling us what that all means. So if we have a to the 1 over n power, meaning nth root of a, and then we have m as a positive integer, if we have a to the m over n power, we can really just split that up and say, well, that's the same as taking a to the 1/nth and then taking that whole thing to the mth power. Again, we're using the idea of multiplying the polynomials when we take multiplying the exponents when we take the power of a power. And so we're just using that in reverse and actually splitting our two exponents up. Now, since we know that a to the 1/nth power is the same as the nth root of a, we could replace that inside of the parentheses and take that to the mth power. That means the same thing. And we can also take that m that's on the outside of the parentheses and we can move it to the inside of our radical. It all means the same thing. All different forms of an equivalent expression. Same thing happens if we end up with a negative m over nth power. The negative simply means that it's 1 over a to the m over n, and then the same equivalents still work, just with the exception that we cannot have an a value of 0. Okay? So keeping those things in mind, let's look at just rewriting expressions back and forth. So here we're starting with radical expressions and we're being asked to rewrite the expression using a rational exponent. So if I have the fourth root of 14, I can rewrite that as 14 to the 1/4 power. The only thing going on here is just that fourth root, and we can rewrite that as a 1/4 exponent. In the second one, however, we're taking the ninth root of 16, but then we're also taking all of that to the fifth power. And so when we rewrite that, we're going to have 16 to the 5/9 power. And the easiest way, I think, to remember this is that the number that we have here is the index, indicates what root we're taking. So when we're talking about writing the fraction as an exponent, I like to think of trees. Trees have roots on the bottom. So whatever our root is here is going to be our denominator here. Same thing here. And then whatever our exponent is on top, that's going to be the numerator. So here there wasn't any other additional exponent, so we just used 1. But here we had this 5, and so 5 is what became our numerator. So when you have those kinds of combinations, just remember that roots go on the bottom and your exponents go on the top. Okay? Now, what if we switch that around? What if we start with the exponential expression and we're trying to rewrite it into the radical notation? So the same kind of thing. When I look at 6 to the 1/3 power, that just means that we're taking the cubed root of 6. So I can rewrite it like this. If I'm taking 10 to the 3/7 power, then the 7 tells me the root, and the 3 on the top tells me the exponent. And I can either write it like this, where I take the 7th root of 10 and then the entire thing to the 3rd power, or I can make 10 to the 3rd power and then take the 7th root of the whole thing. Both of them are legitimate, both of them are equivalent to my first expression. All right, so why don't you take a moment now and work out these problems quick. You're going to evaluate the first two, so you're trying to actually figure out what the answer to those two would be. And then the next 4, you're just going to rewrite them into the other form. So if they're radical, rewrite them as exponential. If they start out exponential, rewrite them as radical. Stop the video for a moment while you try these out and come back when you're ready to check your answer. All right, so for our evaluations, the 4th root of 16 is going to be 2, because 2 to the 4th power gives us 16. And 125 to the 1/3 power is the same as saying 125, the cube root of 125, excuse me. And so that's going to be a 5, because 5 cubed gives us 125. In the rewriting section, the 5th root of 160 is the same as 160 to the 1/5 power. 15 to the 1/2 is the same as the square root of 15. The cubed root of 24 and then all to the 4th power is the same as 24 to the 4/3 power. And 52 to the 6/5 power is the same as the cubed root of 52 all to the 6th power. Or again, you could have had 52 to the 6th and then cubed root, or excuse me, 5th root the whole thing. All right, so now let's put the two together. Let's evaluate what we have using these ideas about what's actually going on. And I would usually recommend that it is easier to take the root before you take the power. So if you're rewriting something that was in exponential form and you're trying to think about it as a radical, take the root part first, then do the power, because you're actually breaking it down into something smaller before you're trying to take the power again. Otherwise, if you take the power first, you end up with really large numbers that might be difficult to figure out what the root is. So for example, when I have the 4th root of 16 and then I'm asked to square that, I actually want to figure out what the 4th root of 16 is first, because that's just 2, and then take the 2 and square it, and I get an answer of 4. So the 4th root of 16 squared is simply 4. In the next one, I have 32 to the 4/5 power. Probably want to at least think about it in terms of radicals. So I'm taking the 5th root of the 32 and then to the 4th power. And I would suggest doing it in that order because the 5th root of 32 is simply 2, and then 2 to the 4th power gives us 16. If you try to take 32 to the 4th power first, although it is possible, it is difficult, and then to try to take the 5th root of that would be mind-boggling. So it usually is much easier to take the root first, then take the power. In our next example, we have 125 to the negative 2/3 power. So we first need to realize that that negative 2/3 means it's 1 over 125 to the 2/3 power. Then we would want to think about taking the cubed root of the 125. That's going to give us 5. Then we can square that, still all in the denominator, and that's going to give us 1 over 25 as our final answer. Okay, so why don't you try a few of those using that same kind of logic that we just talked about. See if you can evaluate these 3 exponential expressions, and when you're ready to check your answer, come back to the video and let's finish things up. All right, so in the first case, we want to take the cubed root of the 64 and then square it. Cubed root of 64 is 4, squared would give you 16. In 81, we're taking the 4th root first, which will be 3, and then 3 cubed gives us the 27. And then in the third example, we have 8 to the negative 2/3 power, which means we're going to have to go 1 over 8 to the 2/3 power. The cubed root of 8 is 2, and then we square that to get the 4, and that 4 is in the denominator. So 1/4 is our final answer. All right, so that's what you're going to be working on in this first lesson. It's just a lot of manipulating the radical and exponential forms back and forth, using them to actually evaluate different expressions, to simplify them as much as possible, so that when we start working with these in actual functions, we'll know how to deal with them. So, you are now ready to complete your practice problems for Objective 3.1 in your booklet. Make sure you're looking for resources to answer any questions that may arise, and don't forget to check your answers once you've completed them on Canvas. If you have any issues or concerns, feel free to contact me through email, and we will see you next lesson.